Okay, so here's the second problem that we're going to solve. Basically, we want to look at the diffusion through a spherical shell, finite thickness, and I'm defining the shell to go from radius r1 to radius r2, and so we have this is the domain we're solving on, and the boundary conditions are that at radius r1 we have a constant concentration of C1, and at radius r2 we have a constant concentration of C2. We're going to say there's no consumption or generation of mass, which means that our little rho sub c is going to go to 0. And we can treat our initial condition as just some f of t, because we're actually going to get rid of that and solve this as a steady state problem. And again, because this is a spherically symmetric system, we're only going to deal with radius, and theta and phi are going to go away. So we start with, again, our flux, and from the flux we also then have a dc by dt, so that's going to be a change in concentration with a change in time defined here, and this is our generation term, which is going to go to 0. The units are mole per meter cubed per second. Substituting flux in, we get this expression for basically this fixed second law. And if we approximate d as constant, which is not exactly true, but is a pretty good first approximation, we get this expression, which is again mole per meter cubed per second. Taking our approximation that there is no generation, so setting that equal to 0, we're left with this partial differential equation. Now, we don't have units yet, but these units are going to be in spherical coordinates, and because of spherical symmetry, the theta and the phi terms in this Laplacian are going to go away, and we're going to be left with this expression, which is the same as we had in problem 1. And in doing this, we've now defined our concentration to be in terms of the radius and the time. And then our boundary conditions can be expressed this way. So at R1, we have concentration C1, at R2, we have concentration C2 for all times. And then we have an initial condition, which is just some function, and as I said, that's going to go away. So this is our problem, but we want to solve this in a very general fashion, so we're going to transform to dimensionless variables. And the first dimensionless variable we're going to work with is dimensionless r, or position. And we're going to define that to be r minus r1 over r2 minus r1, which can be r minus r1 over delta r. This is our dimensionless time, so that's going to be dt over delta r squared, and the units of that come out to be dimensionless. Here we're going to have our chi, which is our dimensionless concentration, and we're defining that is in terms of rho and tau, and that's going to be concentration minus concentration at R1 divided by the concentration at R2 minus concentration at R1, which we now know from the boundary conditions are going to be concentration minus C1 divided by C2 minus C1, which we can write simply as C minus C1 over delta C. So we're defining delta C as C2 minus C1. And in this coordinate system, what that means is that here at R1, we have rho is equal to R1 minus R1 over R2 minus R1, which is 0. And at R2, we have rho defined to be R2 minus R1 over R2 minus R1, which is 1. So now our rho is defined on 0 to 1. And our concentration at C1, we have chi being C1 minus C1 over C2 minus C1, which is 0. And chi at 1 being defined as C2 minus C1 over C2 minus C1 is equal to 1. So our concentrations now also range from 0 to 1 in these dimensionless units. So this is a handy coordinate system that we're going to work with. So we have to take our differential equation and transform it into a problem that's appropriate for this. And we saw how to do this in problem 1. Basically, we're going to have to take all the parts of the differential equation and rewrite them in new coordinates. So here's the partial derivative of time. So that d by dt can be written as d by d tau by dt. Notice these are partial derivatives, these are total derivatives. Tau, we know, is dt by delta r squared. So we have d by d tau times d by dt dt delta r squared, which simplifies to d over delta r squared d by d tau. And then we take chi, and we know that chi is defined to be c minus c1 over delta c, which means that we can write c as being equal to delta c times chi plus 1, or plus c1, which means that when we write out our partial derivative of concentration with respect to time, we get d by delta r squared d by d tau times delta c chi plus c1, which gives us d delta c delta r squared d chi by d tau. So that's going to be on the left-hand side of our differential equation here. Now we have to address the right-hand side, and the right-hand side, when you take d and you multiply through, gives us two terms. The first term here is 2d divided by r dc by dr. So let's go and look at d by dr. d by dr is d by d rho by dr is equal to d by d rho, d by dr, and then we substitute in the definition of rho, right, which is equation 11. And I took that and I split it up just in order to make it easier to see. And when you take the derivative of this, you're left with 1 over dr d by d rho. So that is what these are. And then if we have a rho here, because we got a rho which is going to fit in this as well, or an r, I guess, so it has to go into there. We get rho is equal to r minus r1 over delta r, which means that little r can be written as delta r times rho plus r1. Okay? So that means our first term, which is 2d over r dc by dr, can be written out as 2d, and replacing r, delta r rho plus r1 times 1 over delta r d by d rho delta c chi plus c1, which simplifies to 2d over r delta c by delta r is equal to 2d delta r rho plus r sub 1 dc, or delta c divided by delta r d chi by d rho. So that's the first term on the right-hand side of the equation. And then the second term is d times the second derivative of concentration with respect to position, which can be written like this. And because we already have an expression now for the first derivative right here, we can write this as d 1 over dr 1 over delta r d by d rho, 1 over delta r d by d rho, and then multiply by the concentration, and that gives you this. So that's the second term on the right. It's written out like this when we simplify it. So we take these 14, 15, 16, and we substitute it into 7, and we get this expression. The diffusion coefficient cancels, the delta c's cancel, and then we have a dividing by delta r squared, so we'll multiply across by delta r squared, and that will give us d chi by d tau is equal to 2 delta r, because the delta r there divides out, delta r rho plus r sub 1 times d chi by d rho plus d squared chi by d rho squared. Now this problem is kind of the last place where we have time, because when we get rid of this time, it's going to make things fairly simple, or I don't know if I want to call it fairly simple, but let's say it simplifies it. So we know that for steady state, dc by dt equals 0, which translates into d chi by d tau is equal to 0, which means that equation 17 becomes this, or this. I guess they're the same. I just wrote them twice. This maybe is slightly neater, who knows. But this is now the ordinary differential equation we're solving, and we have these two boundary conditions. We have chi at rho equals 1 equals equal to 1, and chi at rho equals 2 is equal to 0, or sorry, at rho equals 0 is equal to 0. And these are our two boundary conditions, and the initial condition goes away because we got rid of the time dependence, and we're only looking at the steady state solution. So we've got a nonlinear ordinary differential equation with non-homogeneous boundary conditions. So solving nonlinear ordinary differential equations, typically there's no set way. The good news is there are a few functional forms that you can actually do substitution. And this particular equation, where you have the first derivative and the second derivative with something multiplying it that's got the independent variable in it, this functional form can be transformed into a linear differential equation by substituting something. For example, v is equal to the first derivative of chi, and v prime is equal to chi double prime. And we take these and just substitute them into here and to here. What you get is this. And this is a linear ordinary differential equation, and it has the functional form similar to this. This is from an undergrad textbook, something that gets covered basically within the first month of ordinary differential equations. This type of problem has a solution that looks like this. So y is a function of x, and x here is the independent variable. So y as a function of x is equal to some constant times exp of negative integral of the g function dx, where g is the function in front of the variable, dependent variable y, and in this case it's that. So we have a linear problem, and I'm not stepping through all the math here because basically, well, it's pretty tedious. The good news is that because this works, this also means that if you go to Mathematica, it will dump out the solution. So the solution to this problem is chi as a function of rho is equal to rho times r1 plus delta r divided by r1 plus rho delta r. And that is the solution. So we can use this to plot what the steady state solution is for the concentration going from R2 into R1.